Hi everyone, my name is Shani. I spell it Chen and pronounce it Chen, so it's very confusing and I'll probably correspond to every short name that ends with an N. I'm a postdoc researcher at Stanford working with Dan Jurafsky, and I did my PhD with Daphne Shachaf from the Hebrew University of Jerusalem in Israel. I also spent 3 years at Amazon Research and consulted some startup companies. Today I'll present the last paper of my PhD, which I presented 4 months ago at EMNLP in Singapore. This paper is the fun collaboration with Ilis Freyken and Daphne Shachaf, which is my PhD supervisor. In the paper Towards Concept-Aware Large Language Models, we explore whether contemporary language models process language similar to humans and ways to make them more human-like. Large language models, or LLMs, are great, right? They achieve state-of-the-art results across the board and show impressive text handling capabilities. But they're known to be brittle and far from perfect. We argue that some of LLM's problems occur because they operate at the token and not the concept level. This is problematic for even the most fundamental LLM task, which is text completion, affecting their performance on downstream tasks, especially in medicine. One token-based problem is surface form competition, where different tokens of the same concept compete for the probability mass, distorting the ranking. For example, let's consider the mask sentence, "I went to the parent-teacher conference with my There are so many tokens that can complete this sentence with the mum concept, but they're scattered along the ranked list. For example, ma is ranked at 70 and mummy at 88. Because there are so many different tokens that represent the same concept of mum, the probability of each mum-related tokens decreases, and the result is that less likely completions, such as friend and teacher, are ranked higher than they should. But this problem is much deeper than just synonyms. Let's consider the sentence, "I can't get home for the holidays because of the Tokens such as snow, blizzard, and even slippery roads correspond to the same concept that conveys bad weather conditions. Note that these concepts are context-dependent because sometimes snow and slippery roads should not be grouped together under the same concept. For example, you can go and play outside in the snow, but not in the slippery road. These examples help us define a concept as a set of tokens that should be clustered together to convey a meaning given a certain context. Note that this context dependency makes this a really hard problem because we cannot rely on any static knowledge bases. And moreover, concepts have this hierarchy where, for example, we all know that mom is a parent and parent is a family member. So in this paper, we asked 3 research questions. The first one is, how well do LLMs capture concepts? In the second one, we explore whether they match human organization of human concepts. And in the third one, which I'll talk about more deeply than the other 2, we tested ways to enhance LLMs in terms of concepts. We suspect that LLM's lack of concept understanding causes some of the problems I mentioned earlier, and some I didn't mention just due to lack of time. So we set to explore how well contemporary LLMs grasp human concepts. And perhaps the most basic relation between concepts is type of. For example, we all know that corgi is a type of dog, and that dog is a type of domesticated animal. To see how well LLMs capture this type of relation of concepts, we constructed a new dataset and probed 4 state-of-the-art language models. We basically queried the language models to see if they understand that corgi is a type of dog and that dog is a type of domesticated animal. So we used a pre-existing dataset containing 100 everyday things. These are things that we're all familiar with, such as dog, coffee maker, table, tree, etc. But this dataset is flat. So we extracted from WordNet the direct hypernym and hyponym of the 100-day things that are in the dataset. The result is a dataset of the following form. Our everyday thing is a shoe, for example, and then its direct hypernym is footwear, and some of its direct hyponym contain baby shoe, moccasin, sandal, Oxford, and running shoe. If our everyday thing is dog, its direct hypernym are canine and domesticated animal, and some of its direct hyponym are hunting dog, Dalmatian, corgi, poodle, etc. So we use this hierarchical dataset to see whether 4 contemporary language models grasp human concepts, and we used BERT, T5, GPT 3.5, and GPT-4. Now, BERT and T5 were not optimized for question answering, so we used them in a masked way, meaning they receive as input a masked sentence, such as dog is a type of and then we searched along the ranked list of completions for K9. And we did the same for the hyponym level. So corgi is a type of and then we searched for dog along the ranked completions. And we looked at the top 50 completions because these are kind of the most reasonable completions, and otherwise you're just looking at the entire vocabulary. Now, GPT 3.5, GPT 4, and humans, they all support question answering. So we just ask them binary questions. Is dog a type of canine? And is corgi a type of dog? Now, all of these questions are positive. So we wanted to verify that GPT-based models don't have a tendency to just say yes, which will mess up our results. So we also introduced a scramble baseline where we scramble between the everyday things and their hypernym or hyponym. So for example, we ask them questions such as, is corgi a type of vehicle? Is dog a type of plantation? And stuff like that. And for 100% of these questions, the answer was no. So it seems like they don't have a tendency to just say yes. These are our results. Don't be alarmed. I'll explain everything in a second. The y-axis is how well these language models were able to retrieve or find this concept. So higher means better concept understanding. And then the x-axis is the location along the ranked list of completions. So this is only for BERT and T5 because we did not query them using binary questions, but we provided them with masked input, such as corgi is a type of and then we wanted to see where dog would be along the ranked list. And we stopped at k equals 50 just because if it didn't retrieve dog by the 50th location of completion, it will probably not be very likely. So that's why BERT and T5, which are the purple and green curves, change as a function of k, whereas the different curves are just static. So in blue, we can see humans' ability to understand concepts, which is not too bad. It's around 90%, 90 and a bit. And then if we look at the left plot, the hypernym level, that's the dog is a type of K9 level, so the higher level concept, we can say that GPT-4 and GPT 3.5 are very similar to humans, whereas BERT and T5 are kind of left behind. And then if we look at the right plot, the hyponym level, that's the corgi to dog level, we can see that BERT, which is the purple curve, actually takes the lead around 15K, around K equals 15, which is pretty impressive. So we can see that BERT takes the lead, and then we have GPT-4, then T5, and only then GPT 3.5. So our results indicate that LLMs do capture concepts to some extent, but it is far from perfect and from human baseline. And it seems like GPT-based models grasp more general concepts better, whereas BERT and T5 perform better on more specific concepts. To address research question number 2, we also queried to see if language models understand principles such as asymmetry and transitivity. So asymmetry means that if corgi is a type of dog, that entails that dog is not a type of corgi. And we wanted to see whether language models would understand that. So for every language model that was able to retrieve correctly that corgi is a type of dog, we then queried the other direction. Is dog a type of corgi? And we saw that language models do preserve some asymmetry, but again, it's very noisy, it's far from perfect, and that all language models were better at preserving asymmetry for the hyponym level, so the corgi to dog level, better than for the dog to canine level. And this trend was much more significant for BERT and T5. The next principle of human organization of concepts is transitivity. If the model was able to retrieve that corgi is a type of dog and that dog is a type of canine, we checked whether it understands that corgi is a type of canine. So whether it can just skip the dog in the middle and infer that corgi is a type of canine. And our results show that there is some transitivity of abilities in language models, but again, it's very noisy, it's far from perfect. And GPT 3.5 was actually better than GPT-4. BERT was very similar, but slightly behind, and then T5 was way behind. And then for property inheritance, this is for this principle, we actually had to enrich our data set, because in this principle of human organization of concepts, if we know that corgi is a type of dog and dogs are furry, that entails that corgis are also furry, but we don't have this property information in our data set. So we use Quasimodo, which is a common sense knowledge base, in order to enrich our data set with all these properties. And then we use this in order to test our language models using the same mechanism. So similar to the other results, we saw some property inheritance abilities, but again, very noisy, far from perfect. And it was really interesting to see some robustness. So if the model was able to infer that corgis are furry, it was also more likely to infer that canine would also be furry, and the other way around. So it wasn't a matter of a direction from hierarchy. It was more a matter of the language model being able to understand a specific property and then being able to transfer it regardless of the level in the concept hierarchy, which was really interesting to see this robustness that doesn't always occur in language models. And then BERT was actually better than GPT-based models, and and then T5 was left behind. Now, the plots for all of this research question number 2 can be found in our paper. I just don't have the time to go over them. But to conclude research question number 2, GPT-based models seem consistently better than BERT and T5 for asymmetry and transitivity, but for inheritance property, BERT actually takes the lead. However, if we look at all of the models, they all violate the main principles of human organization pretty often, so they show some abilities, but it's still far from perfect, and it shows that they have some inconsistencies as well. So because LLMs do not grasp concepts so well, we move to research question number 3, addressing the issue of making LLMs more concept aware. We explore 2 approaches for making LLMs more concept aware. The first one is about training LLMs with the notion of concepts. In the paper, we sketched a concept-aware training paradigm, and you can check it out there. I will not present it today. Now, I will briefly present our implementation of a proof-of-concept post-processing method to shift any off-the-shelf LLM from the token to the concept level with no further training. This is an illustration of our post-processing manipulation. In short, given a masked sentence, such as I went to the parent-teacher conference with my we augment it by creating paraphrases. We then retrieve the LLM's top completions for the input sentence and its augmentations. And then, to increase the signal-to-noise ratio, we drop sparse completions. Lastly, to form concepts, we perform agglomerative clustering using the LLM contextual embedding. So just to recap this whole illustration, our input is a sentence. We then create augmentations of this sentence by basically just paraphrasing it, creating sentences that have the same meaning but conveyed in a different manner. And then we take the top K completions according to the language model for each of these input sentences, both the original one and its paraphrases, and we use that in order to increase the signal-to-noise ratio. We basically just remove sparse completions, so completions that did not repeat enough time throughout the different augmentations. And then we take all the completions that we're left with, and we use their contextual embedding according to the language model. Why do we want to use the contextual embedding? Because we want to have this representation of the token mom given the input sentence, I went to the parent-teacher conference with my because now the representation of mom would be different compared to a different sentence, such as my gave birth last night. And then we just perform clustering. We use agglomerative clustering, where in this algorithm, each data point is one leaf, and then we have this hierarchy based on our similarity measure. So we use BERT as for our proof of concept because it's an open source model and it's pretty good in grasping human concepts, as we saw in research questions number 1 and 2. And we have our input. For example, I went to the parent-teacher conference with my and then that would be the output of BERT. It's just a ranked list of completions. Now, our concept or manipulation would not output just a ranked list of tokens. It outputs a ranked list of concepts, or basically token clusters that ideally represent human concepts. So the most probable one is mom, mother, mom with a U, dad, father, and then the second one is parents, parent, family, families, folks, etc. And then to evaluate our model, we used a pre-existing data set called ProtoQA. It contains prototypical questions such as name something you're likely making if you buy milk, eggs, sugar, and cream. Now, this is a bit far from the language distribution that language models were optimized for, so we manually changed it into I bought milk, eggs, sugar, and cream to make a and we ended up having 163 sentences. So we ran both BERT and concept BERT on our on the ProtoQA dataset, and we started with a reality check to try to see what's the cluster quality. And to do that, we wanted to measure the semantic similarity, and we did that using word2vec, cosine semantic similarity. So the mean semantic similarity within clusters, so tokens from the same cluster, is 0.41. And then the mean intercluster similarity, so tokens from different clusters, is 0.12. And then just to get a baseline, we also checked BERT's top 10 completion similarity, so the similarity of the tokens in the 10 top ranked completions according to BERT, and this was 0.22. So to conclude, our clusters are both coherent and distinct. Then we wanted to see what's the quality of our ranking, because we created a whole ranking function that is based on these clusters and not on the tokens. So again, we have our input. I went to the parent-teacher conference with my and a completion, for example, parents. We fed that into Amazon Mechanical Turk, which is a crowdsourcing platform, and we asked people to rank whether this completion is likely, ranked as 1, possible but unlikely, ranked as 0.5, or doesn't make any sense, ranked as 0. And we aggregated across different annotators, across different data points. So you can see here some other completions as well. And we used that in order to find the precision at K of both BERT and concept BERT. So we basically allowed our annotators to rank the top 10 completions according to BERT and concept BERT. So according to BERT, that's just going to be 10 words. And according to concept BERT, it's going to be more than 10 words, but that's okay because we can just take the mean of all the words within a cluster. And our annotators had good agreement. The mean variance across the different annotations was 0.17, which is pretty good. And here we can see our results. So the y-axis is the mean accumulated score according to humans, and as we said, 1 is the highest score they can give us, right? This completion is very likely, so higher means better. And please note that the y-axis doesn't start at 0 here. So in purple, we can see the score of concept BERT as a function of location at the ranked list. So we said we're looking at the top 10 completions. So we can see that the completions at the first location are ranked much higher than the others. So it's about 0.95, I'm assuming. And then in green, we can see BERT. So we can see that concept BERT is always better than BERT in matching human intuition. But now we also want to kind of get a sense of what our manipulation actually does. So instead of looking at the top 10 completions and showing that they match human intuition better, we want to look at completions in dispute. So these are completions in which the two language models did not agree. For example, we have this completion for the input sentence, I bought a fake from a street vendor, and then the completion is Jersey. BERT thought that it's not very likely to buy a fake jersey from a street vendor, whereas concept BERT thought that it's very likely. The next sentence is, when I retired, I started the completion is cycling. Again, BERT thought that it's very unlikely, and then concept BERT thought that it's very likely. Now I'm going to go to the end of the table. We have the sentence, I squeezed myself into the completion is sand. BERT thought that it's very likely. Yes, you can squeeze yourself into the sand, and concept BERT thought that it's not very likely. So these are completions in dispute, completions in which the two language models do not agree. So again, we have this input sentence. For example, I went to the parent-teacher conference with my and then we have all of these completions from BERT and from concept BERT. And we're looking for these completions that one of the models thought that they're very likely and the other thought that it's not very likely. So Friends was very likely by BERT, but very unlikely according to concept BERT. Folks was very unlikely according to BERT and likely according to concept BERT, and the same with families. Overall, we had 282 disputed completions. And again, we use the exact same annotation paradigm. We provide annotators with this with the mask sentence and one completion, and we ask them to rank whether it's likely or not likely. Of course, we had the 3 terms. And our mean variance across different annotations was 0.1, so it seems like there is good agreement. Our annotators agree one with another. Now, here are our results. In the first scenario, the first row, these are completions where concept BERT thought that they're very likely and BERT thought they're very unlikely. And the mean score is 0.84. Again, higher means better. And then if we look at the bottom row, this is the scenario where concept BERT thought that it's not very likely, but BERT thought that it's very likely. And the mean score is 0.66. So we have a difference of about 20% in their mean score using human annotators. And then we also annotated a buffer, which are completions where both models agree that they make sense, but they were not in the top 3. And the buffer received a kind of intermediate score between these 2 scenarios, which is 0.74. And then we also use this buffer in order to normalize both scenarios, just because some sentences have a lot of good completions and some sentences don't have a lot of good completions. So we just normalize on a per sentence basis. And if we look at the top row, the normalized score of the scenario where a concept BERT thought that this completion is really likely and BERT thought that it's not very likely is 0.3. And then if we look at the bottom row, the other scenario where concept BERT thought that it's not very likely and BERT thought that it's very likely is actually negative. It's 0.14. So a difference of about 0.4. So to conclude, we tested 3 different research questions. In the first one, we tried to understand whether contemporary LLMs capture human concepts, and it seems like there's some signal to work with, but a lot of noise, and we can improve. We also tested whether they match human organization of concepts, and it seems like it's really far from perfect. And now in terms of enhancing language models, in terms of concepts, when we want to do that with no retraining, so you just need to increase the signal-to-noise ratio and kind of distill this concept awareness that's embedded within the language model, but is really hard to find. And we're actually working on implementing concept-aware training paradigms now. So if you're interested, you can contact me and we'll see if we can collaborate. So if you want to join, please join. Here's the QR code to see the paper. It's an EMNLP paper, so it's going to be on the ACL Ontology website. And here are a bunch of different ways to contact me. If you have any questions or interesting thoughts, I'd be love to hear them now. Thank you.